Okay, so here's kind of the plan because we've only got this week, then next week, we'll meet on Monday night next week, but we won't meet on Wednesday night. College Algebra won't meet next week because of Thanksgiving. And then the week after Thanksgiving, we will meet. And then the next week after that is the final exam. So, I mean, we're almost done here. So there's Celine. I predicted you would get here. So what we're going to do tonight and next Monday. So first of all, y'all are going to be real disappointed to hear this. I'm not going to assign any more homework for this class. Y'all need to focus any homework energy you got on doing homework for the college algebra class, 13, 14. So don't spend time with this 401 homework. What I'm going to be doing in class is just trying to kind of, is that coming from the other campus? Maybe we've got somebody else here. Let me look. Nope, false alarm. Okay.
Because they're not muted.
Yeah, I know, but there's nobody in there. I always wonder why I hear
You're
noises.
echoing because there's nobody.
It's echoing from us, you think?
Yeah.
Probably is. Let me see if I can turn this down a notch. I don't know if that'll help. So at any rate, we're going to cover material tonight that we'll be covering on Wednesday night. I just feel like if you guys placement put you into this class, it won't hurt you to have an extra shot of it. And maybe it'll help us move a little faster on Wednesday night. We'll be doing the same thing next Monday. And then we won't meet next Wednesday. The following Wednesday, that Wednesday after Thanksgiving, we've got to do two things, and we're going to be really up against the time crunch to do it. We have got to finish any loose ends that are in the course, and we've got to go over the final exam review. And so in the middle of all that, I'll be giving you all that take-home assignment. It's the same test I would have given in class if we had had time to do it in class. We just don't. So you'll have a week to do it. Obviously, you'll want to do your best work. I always tell students with that take-home assignment, I don't care if you use your notes. I don't care if you use my math lab. I don't even care if you put a study group together and work on it together. I don't care. Used to, on a take-home assignment, I tried to just, forbid students from doing stuff like that, but all that does is punishes the honest students who try to follow the rules. So the only thing I tell students about that is when you hand that thing in, like I realize that me doing this, you could just find somebody who's really good at math and get them to do your take-home assignment. I get that. But here's the thing, all this stuff that's on the take-home assignment is also going to be on the final exam. And you'll be taking that in class. You won't be able to get help on the final exam. So obviously, if you get help on some of the problems, you need it to be help, not somebody doing it for you, but somebody helping you learn to do it, the problems, because you'll see them again on the final exam. So with that said, for those of you just coming in, we're not doing any more homework in Math 401. You need to focus all your energy on college algebra. Tonight and next Monday night, we'll just be covering college algebra stuff in this class to try to help y'all get ready for what's coming up in the Wednesday class, because we just have such a short amount of time to get the rest of this stuff covered. So with all that said, Chapter 3, now I know I'm skipping over 2.7 and 2.8. We'll pick those up when we need them. I've got to show you enough about those to be able to do. There's a problem from each of those on the final exam, and you'll need to be able to do those problems. So we'll definitely do what we need to do for y'all to know how to do the problems you're going to see on the final exam. But we're just going to jump on to Chapter 3.
So if we don't do the homework in this class, are we going to?
You don't have to worry about the homework in this class. You only need to worry about the homework in college algebra. We don't have time. If you're behind, we don't have time to go back and work on 401. Work on 13, 14. If you pass college algebra, you pass this class automatically. This class is really just here to help you be better at college algebra. So from this point on, whatever time you've got, spend it working on the college algebra course. Don't get so caught up in homework that you don't prepare for tests, particularly that final exam, and you'll be getting your final exam review pretty soon. So at any rate, right now, we just got to get into chapter 3 from college algebra. Section 3.1 talks specifically about quadratic functions. So this looks like a bunch of gobbledygook, but you just need to write it down. I'm going to try to explain what all this is as we go through. Then we're going to look at some examples where we use the information on this page. So a quadratic function, we should kind of have an idea about this by now. A quadratic function is one where we've got an x to the second power term. Everybody see that? So the highest degree term is an x to the second power term. So in chapter 2, section 3, we looked at linear functions. Those were those functions where you only have x to the first power, right? They would look like that. Just y equals something times x plus something. We thought of it as y equals mx plus b because that's the slope and y-intercept. But now the quadratic functions, we add a second degree x term. Just like all of those linear functions have a graph that's a line, right? That's why we call them linear. All quadratic functions have a graph that is a parabola. And so a parabola, kind of a bowl for a U. So a parabola would look something like maybe this, or this one opens, I'm going to say this one opens up. You also could have one that looks like this, that opens down. But every quadratic function has a graph that's a parabola that either opens upward like this or downward like this one. Everybody with me there? So what we want to do, what chapter 3, section 1 is really about is when we see a quadratic function, you know, the equation written out, can we figure out enough information from that equation to draw an accurate graph of that function? Just like when you saw a linear function, you know, it's like, can you pick out enough information from that equation to sketch the graph? So there's several pieces of information we need to be able to draw an accurate graph of a quadratic function. One, we need to be able to know whether it's the parabola that opens upward like this one, or is its graph going to be the parabola that opens downward like this one? And there's a real simple way to know that. If A is greater than 0, it opens up. If A is less than 0, it opens down. So let's talk about what that means in practical terms. If this x squared term is negative, it opens down. If the x squared term is positive, it opens up. Everybody with me there? If the x squared term is positive, it's going to be a parabola that opens up. If that x squared term is negative, it's going to be the parabola that opens down. Every parabola has a vertex. So here's what the vertex is. If you've got a graph that looks like this, let's say, the vertex would be that point on the graph. Or if it's one of those that opens downward, like this one, the vertex would be this point. You could think of it like the vertex is the relative minimum, in fact, the absolute minimum if it's one that opens up, or it's the absolute maximum if it's one that opens down. And we'd like to know exactly what point is the vertex. Like, we don't want to guesstimate. We want to actually know the x and y coordinates of the vertex. And so it turns out there's a real simple way to find those. And this x with the little subscript of v, this just is my way of saying the x coordinate of the vertex point is negative b over 2a. And when we look, say b and a, we mean this b and a. Y'all see what I mean? We're going to see an example in a minute. But whatever that coefficient of the x term is, that goes on top. 2 times the coefficient of this x squared term goes on bottom. And you can think of it like this. Whatever your b value is, reverse its sign. Does that make sense? So if this is plus 2x, then you'd put minus 2 up here. If this term is minus 4x, you'd put plus 4 up here because it'd be the negative of negative 4, right? We'll see that in a minute. Then to find the y coordinate of the vertex, you find f of the x coordinate of the vertex. All that means, I know that looks like real sort of math script or something. All that means is negative b over 2a tells you what the x coordinate of the vertex is. And once you know the x coordinate of the vertex, you literally plug it into the function in place of x to find the y value that goes with it. And that's the y coordinate of the vertex. Everybody with me? Okay. The y-intercept. Where does the graph hit the y-axis? It's c. Whatever that constant term is, that's the y-intercept. The constant term will always be the y-intercept. Remember when we did the linear functions, y equal mx plus b? B was the constant term, and that was our y-intercept, right? So whatever that constant term is, that's where it hits the y-axis. X-intercepts, this is where we have to actually do some math. Because to find the x-intercepts, you have to set this function equal to 0 and solve that equation. So whatever this is, ax squared plus bx plus c, you just write that equals 0, you solve that equation. And we should know at this point ways that we can solve that, either by factoring and figuring out what makes each factor 0, or if it couldn't be factored, we could still find the x-intercepts by using the quadratic formula, right? And you can see why that's true, because when we set this thing equal to 0, what we're really doing is replacing y with 0 and figuring out what values of x make y 0, because all the points on the x-axis have 0 for the y coordinate, right? Okay, so with all that in mind, let's look at an example or two. And let me get some of these papers out from under this so I don't write through on them. Okay, so here's an example. And I'll put this information back up if we need it. So here's a quadratic function, f of x equals x squared minus 2x minus 8. And so what we want to know, we want to figure out, does that graph of, it's a parabola. We know it's a parabola because it's a second degree function. Does it open up or down? What is its vertex? What is its y-intercept? What are its x-intercepts? Once we have all that information, we should be able to sketch a pretty accurate graph of the thing. So is this one going to be one of those parabolas that opens up or one that opens down? Up. Because remember, if the squared term is positive, it opens up. If there had been a minus in front of that x squared, it would be one that opens down. Everybody with me? So it opens up. By the way, remember that means if it's one that opens up like that, that means the vertex is going to be the minimum or lowest point on the graph, right? So sometimes you'll see a quadratic function and they'll say, find its minimum. If they tell you to find the minimum, they're telling you to find the vertex. It must be one of those that opens up and the vertex is the minimum. So now we need to find the vertex. So here we go. The x coordinate of the vertex is negative b over 2a. So notice for us, x squared is the same as 1x squared, right? So our a is 1, our b is negative 2, and our c is negative 8. Everybody see that? where it's ax squared plus bx plus c. So the x-coordinate of the vertex is negative b over 2a. Well, our b is negative 2. Everybody see that? So negative b is going to be the negative of negative 2, which of course is really positive 2, right? Over 2 times a. Well, our value of a is 1, right? X squared is the same as 1x squared. So that's the negative of negative 2, which of course is positive 2, over 2 times 1, which is 2, and 2 over 2 is 1. Everybody see that? So the x-coordinate of the vertex is 1. Now to find the y-coordinate of the vertex, we have to find, y'all look where I'm pointing, we have to find f of 1. In other words, we have to plug the x-coordinate of the vertex 1 into this function. So, I don't know, I didn't leave myself much room to do that. So the y-coordinate of the vertex is 1 squared minus 2 times 1 minus 8. So everybody see that all I've done is plug this x value into this function in place of x. And so that's going to be 1 minus 2 minus 8, which looks like it's going to be, is it negative 9? Right? 1 minus 2 is negative 1, negative 1 minus 8 is negative 9. So now we can say that the vertex is the point 1, negative 9. Everybody see that? It's the point whose ordered pair is 1, negative 9. Y'all look. Here we found the x-coordinate of the vertex, 1. We plugged it into the function to find that the y-coordinate of the vertex is negative 9. So it's the point whose x-coordinate is 1 and whose y-coordinate is 9. Everybody with me? Okay. Before we do anything else.
So the vertex is the solution to the x.
The vertex is a point, and a point is represented by an ordered pair of numbers with, y'all look where I'm pointing, with an x-coordinate and a y-coordinate. So what we did is we found, like, 1 is not the vertex. 1 is just the x-coordinate of the vertex. Negative 9 is not the vertex. It's just the y-coordinate of the vertex. So we plugged in our values of b and a to find negative b over 2a. That gave us the x-coordinate of the vertex. Then we plugged that value, which was 1, into the function in place of x to find that the y value that goes with it is negative 9. That's the y-coordinate of our vertex. Everybody with me? So that is our vertex. Now, we still got to find y-intercept and x-intercepts. Might as well go ahead and find the y-intercept. What is it? If you don't already know, you didn't hear what I was saying about the y-intercept. It's negative 8. The y-intercept is always the constant term. Always the constant term. The y-intercept is negative 8. It hits the y-axis at negative 8. Why is that? In any polynomial function where you've just got something times x to a power or a constant term, all these terms that have x in them, remember the y-intercept is the point on the graph that has 0 for its x-coordinate, right? Well, how would you find the y-coordinate of that? Well, every point on the y-axis has 0 for its x-coordinate. You just plug 0 in for x and find the y value that goes with it. But isn't it obvious that in a function like this, every single term that has an x in it, when you plug 0 in place of x, all those terms become 0, right? And you're only left with whatever the constant term is. So if you plug 0 in for x here, you're going to get negative 8 for y. That's the y-intercept. But you don't have to go to the trouble to plug 0 in for x. You know what's going to happen. The constant term is always going to be the y-intercept. Now, before we look for the x-intercepts, because remember, that's where we're going to have to actually write this equation, x squared minus 2x minus 8 equals 0, and solve it, either by factoring, or if we can't factor it, we would solve it using the quadratic formula. Before we do that, let's take a minute and start graphing the information that we do have. So, we kind of get So negative 1, 2, 3, 4, 5, 8, 9. 1, 2, 3, 4, 5. 1, 2, 3, 4, negative 1, 2, 3. Maybe that's enough. Okay, so here's what we know. First of all, and this is the important thing to know. We know that the graph is one of those parabolas that opens upward, and we know, let me zoom out a little bit. We know the graph is one of those that opens up, and we know the vertex is the point whose ordered pair is 1, negative 9. So there's 1, negative 1, 2, 3, 4, 5, 6, 7, 8, 9. There's negative 9 on the y-axis. So 1, negative 9, that's our vertex. Everybody see that? That's the point, 1, negative 9. Everybody with me? Okay, here's why I wanted to go ahead and plot that. If we go back and look at these parabolas, okay, this one has some x-intercepts. This one has a couple of x-intercepts. Looks like this one has one x-intercept anyway. The question is, do parabolas always have x-intercepts? What if you had one that looked like this? That thing's never going to hit the x-axis. Do y'all see that? So not every quadratic function has a graph that even touches the x-axis. So before we start looking for x-intercepts, it would be good to know if there actually are any x-intercepts. Like, I don't want to write this, x squared minus 2x minus 8 equals 0 out and start trying to factor it. Maybe I can't figure out how to factor it. So then I try the quadratic formula and I do a page of scratch work and then learn that there are no x-intercepts. I'd like to know that before I waste my time looking for them. So remember, this is going to be the parabola that opens up. And here is our vertex. Are we going to have x-intercepts? Put your thinking caps on. It's a parabola that opens upward, and this is my vertex. Do y'all agree that we will have x-intercepts? Because it's going to go up. It's got to cross the x-axis. If this were the vertex, but it was a parabola that opens down, we would know not to waste our time spinning our wheels looking for x-intercepts that don't exist. Y'all see what I'm saying? But they do exist, so we're going to have to find them. I could go ahead while I'm at it, though. Our y-intercept is negative 8, which I guess would be right there at negative 8. So, okay, I want to know, where does it hit the x-axis? So now we're going to figure that out. So for the x-intercepts, you just set that function, which is x squared minus 2x minus 8 equal to 0, and we got to solve that equation. And I believe that this can be factored. And if it can be factored, it shouldn't be very hard to do because it just starts with x squared, right? So we know if it's going to factor, it's got to start with x and x. We know these last two numbers have to have opposite signs. Why is that? Because they multiply to be negative 8, right? If they're going to multiply to be a negative, one has to be positive and the other has to be negative. And then it shouldn't be too hard to figure out that the numbers have to be plus 2 and minus 4. Do y'all see that? Because positive 2 times negative 4 is negative 8, the last number. 2 plus negative 4 is just 2 minus 4, and that's negative 2, the middle number. So what are the two solutions to that equation?
X is negative 2 and x is positive.
Negative 2 and positive 4. Remember, whatever you'd replace x with to make each factor 0, that gives you your solutions. And negative 2 plus 2 is 0, so negative 2 is a solution, and positive 4 minus 4 is 0, so positive 4 is a solution. Those are your x-intercepts. -2, and +4. So let's go back to our graph. So the x-intercepts are -2 there and +1, 2, 3, 4 there. And we know the shape of the graph is a parabola, and I think I've got enough information now to draw a fairly accurate sort of hand-drawn sketch of the graph. You know, on this left side, I'm gonna call this the left arm of the graph. I've got 3 points that I can use. I've got this vertex, I've got this y-intercept, and then I can go up and catch that x-intercept. And so that's what the left side of the graph looks like. Everybody see that? Now on the right side of the graph, y'all look at this, because there's one more little piece of information that we can get real easily. On the right side of the graph, I think I could just realize, by the way, you remember how we were using that parabola to represent y-axis symmetry? Well, this thing doesn't have y-axis symmetry, because notice this vertical line here goes through the vertex. It's going to be a mirror image of itself on either side of this vertical line that goes through the vertex, but that's not the y-axis. Y'all see that? It's 1 unit to the right of the y-axis. But the graph does have symmetry for that line. It's a mirror image of itself on either side of that line. That vertical line that goes through the vertex is called the axis of symmetry. And again, that one we were looking at when we were looking at y-axis symmetry, the y-axis was the axis of symmetry. But it's just wherever the vertex is. The vertical line that goes through the vertex is the axis of symmetry. Here's what that means. So if you just imagine this little axis of symmetry here, notice how this y-intercept is exactly 1 unit to the left of the axis of symmetry. See, that point has x equal to 1. The y-intercept has x equal to 0. It's 1 unit to the left. Then if I go 1 unit to the right, that would put me at this point where x is 2 and y is -8. See, this y-intercept is the point where x is 0 and y is -8. On the other side of that, 1 unit on the other side of the axis of symmetry, you'll have a point where, you know, x is 1, it's 1 unit to the right of that line where x is 1. So 2 equals 2 comma -8. That just lets us pick up another point on the other side of the graph. So now we've got, kind of like how on the left we had 1, 2, 3 points to guide our pencil. Now we've got 1, 2, 3 points on the right to guide our pencil as well. It would look better if I'd drawn that up farther, but that's what our graph looks like. That's our particular parabola. One last thing about this axis of symmetry, because you may see a couple of homework problems where they ask you to actually tell them the axis of symmetry, where they literally say, what is the axis of symmetry? The axis of symmetry, remember, is a vertical line. And every vertical line has an equation that looks like x equals some number. And that, for the axis of symmetry, that number is always going to be the x coordinate of the vertex. So the vertical line x equal 1, that is our axis of symmetry. Everybody see that? So if you run into a homework problem where they're asking you to find this information and check the graph, if they ask you for the axis of symmetry, it's always the vertical line x equals whatever the x coordinate of the vertex is. In this problem, 1. Everybody see that? So this is basically what we do to graph quadratic functions. We take a look at the highest degree term because we want to know if it opens up or down. It's really good to know that before you get started. But you just have to look at the squared term to know that. You want to find the vertex. The constant term always gives you the y-intercept. You want to check and make sure there are x-intercepts, and assuming there are, you then set that function equal to 0 and solve it, either by factoring or, again, if it couldn't be factored, you could use the quadratic formula. That gives you your x-intercepts, and then your axis of symmetry. It just helps you maybe get one more point without having to start plugging numbers in to find a bunch of points. Let's look at one more example. We're just going to go through one more example just so y'all kind of see what this process is. Of course, Wednesday night we'll be going through a couple of more, and I'll try to make sure I use different problems just so you get some more in your notes. Okay, so here's another one. And notice the only difference really here is, in terms of how it looks, is this time instead of saying f of x, I said y, but it doesn't matter, right? It's the same thing. So y equals negative x squared plus 4x minus 5. So is that parabola going to open up or down? Down, because our squared term's negative. Y'all see that? So we know it opens down, which means that the vertex is actually the maximum or highest point on the graph. Everybody with me there? And now we want to find the vertex. So the x-coordinate of the vertex is negative b over 2a. So notice our a is negative 1, because negative x squared is the same as negative 1 times x squared. Our b is 4. Our c is negative 5. So, okay then, the x-coordinate of the vertex is negative b. That's going to be negative 4. Over 2 times a, that's going to be 2 times negative 1, right? And that's negative, 2 times negative 1 is negative 2. So that's negative 4 divided by negative 2, which is positive 2. Everybody see that? Now that we have the x-coordinate of the vertex, we're going to find the y-coordinate of the vertex, and we're going to do that by plugging 2 into this function in place of x. 2 is our x-coordinate. To find the y-coordinate that goes with it, you just plug it in and find the y value, right? So we'll have the negative of 2 squared plus 4 times 2 minus 5. Be careful when you calculate this. This is not actually negative 2 squared. Everybody look where my fingers are here. Remember, x is 2. So if I plug 2 in here, 2 squared is positive 4. But this minus is in front of that, which would then make it negative 4. Do y'all see that? This isn't negative x all in parentheses squared. This is the negative of x squared. And so 2 squared is 4, but the negative of that is negative 4. And then 4 times 2 is positive 8 and minus 5. And so negative 4 plus 8 is positive 4. 4 minus 5 is what? Negative 1. So now we know our vertex. It's the point whose x-coordinate is 2, right? And whose y-coordinate is negative 1. Okay, so let's do kind of what we did a minute ago. Let's kind of begin.
Can you slow down just a little?
Yep.
Okay, that, where it says y equals 2 squared plus 4, all that, what is that symbol right there by the 4? I mean, not by the 4, by the y. Is that a b? What is that?
This x,
No.
so listen,
Yeah.
x sub v means the x-coordinate of the vertex. Y sub v means the y-coordinate of the vertex. Everybody see that? The subscript of v is just because I didn't want to write y-coordinate of the vertex, x-coordinate of the vertex. I just use a subscript as shorthand to say this x with a subscript of v is the x-coordinate of the vertex point, and this y with a subscript of v is the y-coordinate of the vertex point. Everybody with me? Does that make sense? Okay. And again, what's the y-intercept? Negative 5. So Got that much information. So now I'm going to go ahead and kind of, graph, go ahead and sketch the part of the graph that we know about so far, because again, I don't want to look for x-intercepts if there actually are not any. So if I start to graph this thing, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. 1, 2. Okay, so 2, -1 is our vertex. So there's 2, go down 1, there's -1. That's our vertex, 2, -1. Everybody see that? Are we going to have x-intercepts?
No.
No, we won't. And why is that? Because it goes down. This is the highest point on the graph. It only goes down from here. It's never going to hit the x-axis. Everybody see that? Okay, so that's a good thing in one way, because it means we don't have to spin our wheels. What if we didn't know that? What if we didn't take the time to think about our vertex and how the graph opens? So we just assumed there were x-intercepts. So here's what would ultimately happen. And I'm going to go down this rabbit hole, even though I really don't have time to, but I just want y'all to see what would happen. So if I tried, I would say, okay, so the negative of x squared plus 4x minus 5 equals 0. Now I would try to factor that. And I would probably spin my wheels for a little while, only to eventually decide I don't think it can be factored. Then I would have to use the quadratic formula. I'm going to go through this quadratic formula super fast because A, y'all seen it, and B, all I want for you to see what happens when I use the quadratic formula. So x equals negative b, that's -4, plus or minus the square root of b squared, that's 4 squared, minus 4 times a, which is -1, times c, which is -5. And that's all over 2 times a, which is 2 times -1. And then I would keep going, and I would get -4 plus or minus the square root of. Okay, 4 squared is 16. Everybody with me there? When you do this minus 4ac part, -4 times -1 is +4. +4 times -5 is -20. So I get 16 minus 20, which is -4 under that square root, right? I know I'm going fast, but just if you take the time to do the math here and you do it carefully, you're going to see that you get -4 under that square root all over 2 times -1, which is -2. So then I would have -4 plus or minus. Okay, what is the square root of -4? What is the square root of +4?
It's 2.
Okay, then what's the square root of -4? 2i. We've talked at some length about that. In fact, we spent more time on it than we should have. That's why we're rushed now. And that's all over -2. So I could cancel a 2 from every term. And I would get -2 plus or minus I all over -1, which is to say actually negative over negative is positive. So it'll be 2 plus or minus I. So that's what I get when I try to solve that equation equal to 0. Notice those are not real numbers. They're solutions to that equation. We saw some of these back in section 1.5. Those are perfectly valid solutions. They happen to be complex numbers. But remember, when we're graphing an equation, we're graphing in the plane of real numbers. There are no non-real numbers showing up here. That's why this thing has no x-intercepts. Or the fact that it has no x-intercepts is why the solutions to that function equals 0 are non-real numbers, however you want to look at it. So here's what we know. The y-intercept is -5, right? So negative 1, 2, 3, 4, 5 right there. Now here's where this axis of symmetry comes in handy, because since we don't have any x-intercepts, we have only 2 points to guide the left side of this graph, to guide our pin on the left side of this graph, but we only have the vertex. We don't have any points to help us figure out what the right arm of this graph looks like, right? But what I could do is say, okay, well, wait a second, my axis of symmetry goes through that point where, remember, x is 2, y is negative 1, so x equal 2, that's our axis of symmetry. Notice this y-intercept is 2 units to the left of the axis of symmetry. Well, if I go 2 units to the right, I'll also hit a point on the graph. And so that would put me here. See, I would go 2 units. So from where x is 2 to 3 to 4, x is 4. And of course, I'm going straight across from this point where, remember, that's our y-intercept where y was negative 5. So it puts us at the point 4, negative 5. I guarantee you, I'm not going to take the time to do it because we don't have the time, but I guarantee you that if you were to plug 4 into this function in place of x and calculate the y value that goes with it, you would see that negative 5 is the y value that goes with it. At any rate, now I have at least enough information to draw a reasonable sketch of the graph, right? And there's our graph. And that's all I'll require you to do. You could, if you wanted your graph to be like hyper accurate, what you could do is you could pick a point, like maybe you could pick an x value, like you could plug maybe 6 in for x and, you know, plug it in, find the y value that goes with it. You know, it'd be a point down here somewhere. Then you'd have another point to help you draw your graph, and you could then say, well, that point is 6 units to the right of the, it's 4 units. It's 4 units to the right of the axis of symmetry, right? We went from where x was 2 up to where x is 6. Then if you went 1, 2, 3, 4 units to the left of the axis of symmetry, that would give you another point over there. So you could keep doing that, but really you need the vertex, the x and y intercepts, if there are any x intercepts. You need at least 2 points on either side of the graph. In other words, the vertex and at least one other point on each side of the graph. And if you have that, that's enough to sketch the graph. Everybody see how to do that? So look, we're going to see a couple more examples of this Wednesday night. And again, I'll try to use different functions just so you can get some notes on a couple of other examples. But that's what's going on in 3.1 is how do we, when we have a quadratic, a second degree function, how do we sketch its graph, which comes down to, can we determine how the graph opens up or down? Can we find its vertex and y-intercept? And can we determine if it has x-intercepts? And if it does, can we find them? Yes.
So going back to the first one,
Mm-hmm.
when it did have an x-intercept,
Mm-hmm.
when we're solving it, do you want us to use the quadratic formula?
Not unless you can't factor it. But obviously, if you can't factor it, you'd have to. That'd be the only way to do it.
Right.
And then if you're actually trying to draw the graph, you know, here's another thing I would say about that. You know, when you're, you know, let's say that you, well, in fact, let's just look at this one that you did, where we didn't have any negative. So when we did that one, when we did this one here, and we found, when we solved that, well, let's do one where you do have to use the quadratic formula. How about that? Where it has x-intercepts, but it can't be factored. So let me see if I can come up with something. Y equals, let's say, x squared minus, now let's say 6x plus 1 equals 0. Plus 1. Let's say we want to graph this. Okay, so it opens up. I'm just going to zip through the parts of this we've done. It opens up. The x coordinate of the vertex is the negative of -6 over 2 times 1, which is 2. And that's positive 6 over 2. So the x coordinate of the vertex is 3. The y coordinate of the vertex is going to be whatever I get when I plug 3 in. So it's going to be 3 squared minus 6 times 3 plus 1. 3 squared minus 6 times 3 plus 1, right? That's 9 minus 18, which is -9. -9 plus 1 is what? -8. So our vertex, the x coordinate is 3. The y coordinate is -8. So we know it opens up. Now we know its vertex. The y-intercept is the constant term, which is 1. The x-intercepts, again, we'd probably want to graph the vertex and think about how it opens up. But I can tell you it's going to have x-intercepts. I've made sure it did. So the problem is x squared minus 6x plus 1 cannot be factored. It's not factorable. Like if I tried to factor the thing, like to solve this equation, I'd have to have two numbers that multiply to be +1 but add to be -6. Do y'all see that's not possible? So I've got to use the quadratic formula. So negative b is going to be the negative of -6 plus or minus the square root of b squared. That's going to be -6 squared. Now that is -6 squared. So notice that's going to turn out to be +36 minus 4 times a, which is just +1, times c, which is also +1. And that is all over 2a, which is just 2 times 1. And so when I simplify this, the negative of -6 is +6, plus or minus the square root of -6 squared is +36. I'm doing some scratch work here. -4 times 1 times 1 is -4. So I'm going to have the square root of 36 minus 4, which is the square root of 32, all over 2 times 1, which is 2. I can simplify the square root of 32 because 32 is the same as 16 times 2, right? So I know what the square root of 16 is. It's 4, right? So the square root of 32 then is the same as the square root of 16 times the square root of 2. And I know what the square root of 16 is. It's 4. So I get 4 times the square root of 2. So here's what I've got. I've got 6 plus or minus 4 times the square root of 2 all over 2. Because 2 is a factor of every term. Now notice 2 is not a factor of the square root of 2, but it is a factor of 4, right? So I'm going to cancel a 2 from every term. That becomes 1. 2 goes into 6 3 times. 2 goes into 4 2 times. I get 3 plus or minus 2 times the square root of 2. Those are my x-intercepts. And if there's a problem in homework where they ask you to find the x-intercepts, they're going to want these exact answers. But the reason I wanted to do the problem is because I wanted to show you all this. When you actually graph something like this, here's the thing. When we graph this thing, so when you actually graph this thing, so our vertex was 3. Oh, I got to go farther down, don't I? -5, 6, 7, 8. So our vertex, remember, was 3, -8. So that would be about here. There's our vertex. Our y-intercept, remember, was 1. That's going to be here. It opens up, so it does have x-intercepts. Here's the problem. Our x-intercepts were 3 plus or minus 2 times the square root of 2. I don't really have a good sense of exactly where 3 plus 2 times the square root of 2 is on this x-axis. Y'all see what I'm saying? So this would be a thing where probably what you would have to do is get out your handy dandy calculator and you would have to punch those numbers in. Don't tell the homework that whatever you get is your x-intercept because it'll be an approximation, but you'll probably have to get approximations to know where those kind of where they're located. So I could do that if I just get out my, let me turn that out. Oh, wrong one. There. So if I just punch in 3 minus 2 times, did I hit times? God, I can't see.
Yes, you did.
Times the square root of, times the square root of 2. It tells me that that's like 0.1715, blah, blah, blah. Y'all see that? So that's going to be somewhere positive, somewhere just a little bigger than 0, about there. And then if I do 3 plus 2 times the square root of 2, it tells me that's like 5.83, which will be 4, 5, somewhere right about there, right? So you might have to, you know, if you have to use the quadratic formula and then you actually have to draw the graph and plot those, you probably will have to punch those numbers in and get approximations just so you know about where to put them. But once you have that, you know, you can draw the graphs. That makes sense? I will tell y'all on that take-home assignment that you'll be getting for test 3, you won't have one on there where you have to use the quadratic formula unless you just can't figure out how to factor it. But if it's a problem where it has x-intercepts, it'll be something you can actually factor, you know, unless you just can't not able to factor or whatever, but it'll be factorable, I guess I should say. Okay.
Will the final have the quadratic formula, or is it take home assignment going to be kind of like the review for the final?
No, the take-home assignment is test 3 over the material we're covering starting tonight. The final exam covers everything in the course, which is why we got to haul our butts and try to get through this material. Okay, moving on. We'll look at a couple more examples of that Wednesday night, but we've got to move on. Once we get out of section 3.1, once we get to section, this is in the college algebra course, of course. Once we get to section 3.2, we just look at polynomial functions. So linear functions are first-degree polynomial functions. Quadratic functions are second-degree polynomial functions. Now we're just going to look at polynomial functions in general. It might be a second-degree function or a third-degree function. It might be a 10th-degree function. We're just looking at them in general. So a couple of things I would say before we start getting into all this kind of mess is, first of all, you know, we've already seen that when we're graphing, you need to know something about what the graph looks like before you ever start drawing the graph. So for example, in section 2.3 that we had in this last chapter, where you only have like y equal mx plus b, we knew that the graph was going to be a line. Well, that's important to know. We know the shape of the graph before we ever try to graph it, and knowing that tells us that we really only need to find 2 points on the graph to sketch the graph, right? Because there's only one line that goes through 2 points. If you didn't know the graph was a line in advance, you might think you needed to plug in 6 or 7 different x values and find the y values and so on. Now we've seen with those second-degree functions, we always know the graph is a parabola. Well, it's important to know that because once we realize the graph is going to be a parabola, then we know that we can find just a few pieces of information, the vertex, the x and y intercepts, think about how it opens, and sketch the graph. So it kind of lets us know what we need to do to be able to graph it. If it's just a polynomial function in general, I mean, the graph could be anything. So really what we're doing for most of the rest of what we're going to do tonight is looking at how can we begin to get more specific information about what a function's graph should look like, what the basic shape of the graph should be. And so the first piece of thing we're going to learn is polynomial functions graphs are smooth continuous curves. Now that doesn't tell us a whole lot, because smooth continuous curves, there's a lot of different things that could be. Like for instance, there's a smooth continuous curve, about as smooth and continuous as you can get. We know that first degree polynomial functions tend to look like that too, right? Or this is a smooth continuous curve. A parabola is an example of a smooth and continuous curve. But this is a smooth continuous curve. And this is a smooth continuous curve. And this is a smooth continuous curve. And, you know, that's a smooth continuous curve. And you could just keep drawing as many. Smooth continuous means you can draw it without ever lifting your pencil. And it's got arrows on both ends. That's what continuous means. Smooth means that there are no breaks in the graph, which goes along with continuous. There are also no sharp edges. In other words, you would never have something do like that, for example. Any graph that does that, it might be a graph of some function, but not a polynomial function.
Yeah, see that? Can you move your down so we can see it? No, down so we can see the top. There you go. Perfect.
That couldn't be the graph of a polynomial function because it's not smooth. But any of these could be the graph of a polynomial function. So if you just see a polynomial function in general, if it's first degree, you know it's going to be some kind of line. If it's second degree, you know it's going to be some kind of parabola. But what if it's fifth degree? What if it's fourth degree? What if it's seventh degree? What if it's 23rd degree, et cetera? Well, at some point you're like, okay, it might have any number of, humps and dips and, so on and so forth. So we're going to start trying to zoom in and find more specific information about these various functions graphs. So first of all, the graphs that you see on this screen, you can see them all at once. The graphs you see on this screen, they all look pretty different. But some of these graphs have features in common with other graphs that are on this page. So for instance, these two graphs have a feature that's in common. They have a feature that both of them share that's kind of the same. What is it? I mean, this one's a straight line, this one's not. But what is it that's similar with both of them?
They both have arrows.
Well, all of them have arrows, but what about the arrows that these two have? You're on the right track. Like this one has arrows and this one have arrows, but the arrows aren't the same. Here they are. The arrow's going down on the left and it's going up on the right, and it's doing that in both of those graphs. Do y'all see that?
Oh, that makes sense.
Y'all see what I'm saying? So they're both going down on the left, they're both going up on the right. So that's something they have in common. I mean, obviously they look very different from each other in the middle, but on the ends they look the same. Do y'all agree that these two all look the same on the ends, right? We're going up, up, and up, up. Now, this one on the end is going down, down. We don't see another one that's going down on both ends. This one's going up on the left and down on the right. And that's different than these that are going down on the left and up on the right. Does everybody see that? But if you look at this, what's happening with these arrows on the ends of the graph is called the end behavior of the graph. And so what you should pretty quickly see is there's 4 possible end behaviors. It could be falling on the left and rising on the right, or it could be rising on the left and falling on the right. or it could be rising, going up on the left and the right, or it could be going down on the left and the right. So the first thing we can do is we can figure out how we can just look at the equation and immediately know what the end behavior is for the graph. Kind of like how with those quadratic equations we just looked at, you can just look at the equation and immediately know whether it's going up on both ends or down on both ends, right? That's an example of figuring out end behavior. Or with these linear functions, remember if the x term was positive, you know, where you've got y equals mx plus b, and if m is positive, in other words, that x term's positive, it's going to be a line like this that rises from left to right. In other words, it's going down on the left and up on the right. If this x term was negative, if our slope was negative, it would be falling from left to right. In other words, rising on the left and falling on the right. Everybody see that? Well, we want to be able to determine that for any polynomial function, regardless of the degree, whether it's first degree, second degree, 20th degree, 17th degree, or whatever. And so here are some examples of polynomial functions. And it turns out, and these look kind of complicated, it turns out that every single one of these, you can look at it and immediately know what's happening on the ends of the graph. And so now I'll show you that little table that I hastily scribbled up. So there's two things you're looking at. They call this the book calls this the leading what we're about to look at, they call it the leading coefficient test. I think it would be easier to think of it as the leading term test. You're looking at the highest degree term. Like in this f of x, the leading coefficient is just the number -3. It's the coefficient of whatever that variable term is. Really, we're not just going to look at that number -3. We're going to look at that entire term, -3x to the 6th. So I'm going to say that I like to call this the leading term test. There's two things you're looking for. You're looking at only at the highest degree term. You're looking at the degree of that term. And what I mean by that, what you're looking for is the highest degree term's degree even or is it odd? So notice here, -3x to the 6th. Well, 6 is an even number. The highest degree term is even. Everybody see that? Or 2x to the 5th. 5's an odd number. The highest degree term is of odd degree. Y'all see? So you're looking to see if the degree of that highest degree term is even or odd. Then you're looking at the sign of that highest degree term to see if it's positive or negative. And here are the rules. These are all the rules for end behavior. Let me kind of see if I can block those out where you can see it a little better. This is it. If the highest degree term's degree is even and the sign of that term is positive, so the highest degree term is positive, the end behavior is up on both ends. So look at, for example, let's see if I can find one. Look at h of x. So the highest degree term is 4th degree. 4 is an even number. The highest degree term is positive, right? It's positive x to the 4th. Well, then that means that h of x is one of these where the degree is even and the sign of that highest degree term is positive. Y'all see that? Then the end behavior of that graph is going to be up on both ends. Everybody with me? Now, I don't know what's happening in the middle of the graph, but I know on the ends it's going up on both ends. Everybody with me? If the degree is even, but the term itself is negative, it's going to be down on both ends. So notice if the degree is even, it's either up on both ends or down on both ends. And you determine which it is by whether the term itself is positive, up on both ends, or negative, down on both ends. That's exactly how it is for those second degree equations we just looked at. And of course, the highest degree term is even degree. So if you look at f of x, Notice the highest degree term is 6th degree, but the term itself is negative, right? Then that means that one's going to be down on both ends. Everybody see? Okay, if the degree is odd, so notice g of x and j of x, both of them, their highest degree terms are odd. 5th degree and 3rd degree, those are odd numbers. If the degree is odd and that highest degree term is positive, then the end behavior is it's going down on the left and up on the right. So let's see, degree is odd and the highest degree term is positive. That's g of x. Do y'all see that? G of x is 5th degree, so the degree is odd. The term itself is positive 2x to the 5th. So the degree is odd, the term is positive, the sign in front of the term is positive, then it's down on the left and up on the right. Finally, if the degree is odd, but the sign of that highest degree term is negative, it's up on the left and down on the right. So notice j of x, the degree is odd, it's 3rd degree. Y'all see that? The term is negative. That means that if I were to graph j of x, the graph would be going up on the left and down on the right. Everybody see that?
Will it always have a degree?
If it's a polynomial function, it has to, because every term looks like x to a power or is a constant term, right? I mean, the degree might be 1st degree. It might be 2nd degree. It might be 3rd. It might be 4th. It might be 37th. It's just whatever the highest degree x term is, that's the one you're looking at. You're looking to see, is that exponent even or odd? And then you're looking to see, is that highest degree term positive or negative? And then this little chart tells you what's happening on the ends of the graph. And if I just take a minute, we'll take a break here in a minute, but if I just take a minute, I'll show you some of these graphs and you'll see that our prediction based on this is going to be right. Let me swing by here and just check and see if, okay, nobody ever made it from Paris, but I wanted to make sure. Let me see if I can bring up Wolfram Alpha and I will show y'all some of these graphs and you can see. Let's see if I can get there quickly. Okay, let me switch over from the document camera. Give me a second. We'll take a look at these. We're going to stop sharing that. We're going to start sharing Wolfram. Okay, so there's Wolfram Alpha. I'm going to put some of these in. I'm going to start with J of X, the bottom one, just because it only takes a second to punch it in. Some of these are pretty long-winded. So let me punch in J of X equals negative 2x to the 3rd plus 8x. Okay, and let me tell it to operate on that. So I don't want to show you the graph just yet. But there's the function, negative 2x to the 3rd plus 8x. Everybody see that? Okay. Remember, we predicted that j of x, based on the fact that it's 3rd degree, which is odd degree, and the highest degree term is negative 2x to the 3rd, then we predicted that the graph's going to be going up on the left end and down on the right end, right? I can tell you a little bit more about this, by the way. This graph also has symmetry. What kind of symmetry is it going to have? Is it an even or an odd function? It's an odd function, right? It's only got odd degree terms, 3rd degree, 1st degree. Then its graph should have origin symmetry. So see, I know quite a bit about this graph without ever looking at it. And I haven't really done any math to figure any of it out either. I know it's going up on the left, down on the right, and I know it should have origin symmetry. And sure enough, there it is, up on the left, down on the right, and you can see if I flip this upside down, it'd look the same, right? And of course, that helps us too if we're trying to graph it, because if we know that it's up on the left, down on the right, and we know that it's an odd function, then y'all follow my cursor here. If I could just figure out what that part of the graph looks like, Like if I could figure out what the graph looks like on the left side of the y-axis, then I could just flip that over on the right side of the y-axis, and that would be the graph. Do y'all see that? Like I wouldn't actually have to figure out a bunch of points on the left side of the graph and then plug in a bunch of numbers to figure out a bunch of points on the right side of the graph. Because if I know what the left side of the graph looks like, well, I know what the end behavior is over here, and I know it has origin symmetry, which means whatever this is, if I just flipped that upside down and moved it over to the right of the y-axis, that would finish my graph. So just pointing out that sometimes knowing these things makes it a lot more efficient to graph. So let's look at one of the even functions. Let's say we looked at that f of x, which if you've written it down, if you don't, I'm about to punch it in. So f of x was equal to negative 3x to the 6th plus 9x to the 4th plus 7x squared plus 4. Oh, and I just realized something that I actually either hadn't noticed or had forgotten about. That thing has y-axis symmetry. Make sure I'm right on that. So there it is. This is going to have y-axis symmetry. Do y'all agree that that's an even function?
We wouldn't keep the j of x, correct?
I'm sorry?
In the equation, you have j of x.
Oh, yeah, I need to get rid of that. Let me get rid of that.
Get rid of it, right?
Yeah, let me get rid of that. Doop. So it should have y-axis symmetry, but also notice it should be going down on both ends. Do y'all agree? The highest degree term is x to the 6th, and 6th is an even number. And that term is negative 3x to the 6th. So if the degree's even and the term itself is negative, it's down on both ends. And this one happens to be an even function. And sure enough, there it is going on down on both ends. And can everybody see that it's a mirror image of itself on both sides of the y-axis? So I'm not going to do the other ones, but I could. We'd see that the end behavior, that little test. Let me go back to our document camera. No, don't want to do that. Cancel. Okay, so you can see then that this little table here tells you everything about what's happening on the end of the graph. And so we're going to take our break here in a second. And when we come back, what we're going to kind of work on just a little bit is we're going to begin to look at, okay, once I figure out what's happening out on the ends of the graph, now I've got to zoom in and figure out, okay, how do I figure out, you know, what it looks like between the ends of the graph. And so that's a little more detailed stuff, and that's where we have to do a little bit of work here and there mathematically to figure that out. Let's take a break. It is, let's just call it 7:15. So 7:25, we'll get rolling again. I'm going to pause the recording, and y'all help me remember to start it back when we get back.